Hi, everybody. This is Nalini Elkins with Industry Network Technology Council. If somebody can please let me know if you're hearing me okay, that will be good. And if you have a problem, of course, please let me know during the course of the webinar. Yes. Okay, great. Thank you. Yeah, I'm hearing that the sound is okay. Perfect. Thank you so much. This webinar is being recorded just so that you know. And of course, the presentation and everything will be made available to you at the end of the webinar. So let's go ahead and get started. So here's just a couple of words about me. We'll just go past that quickly. I've been in the industry for a long time and working with IPv6 for a good deal of it. I am the president of Industry Network Technology Council. Okay, we will have a special treat today. We will have some of the students that we have been working with at the National Institute of Technology in Karnataka, NITK Surathkal, and they will tell you they have been a great help in helping to do some of this testing. So it'll be a great treat to hear from the students themselves. Okay, so what we're going to talk about today is some of the address structure and where extension headers fit into the whole IPv6 architecture. Then we'll talk about some of the testing we've done, both standalone and the interaction with CDNs, and then the students will talk. So you can see here, just stepping back, the IPv4 main header is, of course, a 20 bytes, and the IPv6 main header, which is 40 bytes. And of course, the main header is quite a bit bigger for IPv6 because the source and destination address are so much bigger. In fact, 4 times as big as the original. I think people were thinking, let's make it really big because we don't want to go through this pain again of doing the transition, which quite a few people have not even done. Oh, there we are. But some of these fields are quite interesting. In particular, to my mind, the IPID field, which is used originally for fragmentation, but which many people use for diagnostics. And so what has happened to some of these extra fields is that they have been moved into an extension header. You'll see here, let me get my little highlighter out. So you'll see here the next header field. IPv6 does what is called header chaining. And so that means that you have not only the payload, but you can have multiple headers in the main header itself to do various functions. And now this is the crux of a somewhat heated at times controversy at the IETF about whether extension headers can be used, should be used across the internet. So there are some rules for how extension headers are to be done. Each one points to the next. So you have to have a fixed order, which is of course defined in the main IPv6 RFC. You have where the first extension header goes, it points to the next, and so on. Clearly, you can see a number of problems here, which is that if you have too many, then what you're going to be doing is doing nothing but sending extension headers. And ideally, what we're doing is we're sending data in the payload to do some type of function and not just doing network management or security or other functions, metadata, if you will. So there is a valid point to be made there. So what are these extension headers? Well, these are the common ones. There are some other ones that are being defined. The first one is hop by hop. This is potentially one of the most controversial ones. I would say hop by hop and routing, the routing header, are both somewhat controversial in that each device along the path has to look at the hop by hop header. And so some people feel, well, that will add quite a bit of latency to the traffic. It's also extra load on the routers and network devices along the path. Of course, that is a good point. The routing header was one of the routing headers was deprecated because it could be used to do an attack. There are some other things that are being defined for that. The fragment header is quite interesting. In IPv4, fragmentation was done in the main header for IPv4 itself, and that is why you had IP ID and the fragment count. So fragment headers are now, fragmentation can only be done by the source, which is the sender or receiver. Sender. It's source fragmentation only, and the receiver unpacks it. And so that speeds things up because the routers don't have to use it. But once that was done, one of the fields we used for diagnostics disappeared. And so then we'll talk about how we are attempting to get that back and actually have an RFC to that effect. ESP and AH, you may know from doing IPsec. These were backported to IPv4, and so they are essentially the same on both. Destination options is one of my favorites because this is really, in some ways, what gives the most flexibility to IPv6. It allows the destination itself, the source, the server, or the client, to put in something which will be decoded by either end. It's information from both ends, and that can be very, very useful for many reasons. Even many things that we can't foresee in the future might be done via destination options. So here's a little pocket trace, and you can see the hop by hop option, and you can see it has here header, which is hop by hop, and then here is the header itself, and then within the hop by hop header, it points to the payload. In this case, it is ICMP v6. And interestingly enough, you'll see, of course, that destination options can be used on multicast as well as unicast. So that makes it quite useful to be able to have extension headers. So here's the destination options that we were talking about, and you can see the idea is that the source creates a destination options. It goes through the network, and the destination unpacks it and looks at it. The routers along the path are really are supposed to just pass it along. They're really not even supposed to be looking at it. And so here's the use of destination options in mobile v6. And you can see here, it says right away, the next header is IPv6 destination option. And this is a source address, which is a unicast address. And it has then the destination option itself going on. Destination options is one of, I believe, one of the only headers where you can, or maybe the only header where you can have more than one destination option. And I have seen people do that. It is, of course, unfortunate that mobile IPv6 has not had more penetration, but that's a topic for another webinar. So let's talk about the issues with extension headers, and then I'll talk about the pros. I am an IPv6 extension header proponent. One might even say bigot. I think they are one of the things that makes IPv6 very compelling and will allow it to live for many, many years to come. And that's why I've spent a good deal of time in the past year and a half, 2 years with this, and there is more time to come. And I have been fortunate enough that I have a very good team, and there are quite a few others, some of whom are on this call, who also are proponents of extension headers. And so at the end, we may be able to have an interesting conversation with everyone. So let me give you the potential issues with extension headers to be somewhat, doing both sides, somewhat even-handed. So the issues are routers or something in the middle of the network. Frankly, we have not seen routers dropping extension headers. There was one we tested which had a bug in the router code, and it dropped it. By and large, we have not seen routers dropping extension headers. They appear to be passing them swiftly on. This is not to say we may not find this in the future, but we've not seen that. What we have seen is things like load balancers potentially dropping extension headers. It may be because there are bugs. There was one bug we did find in a major CDN network where there was a problem with a load balancer. They have fixed it, and everything now works to an extent. I will talk about CDNs later. So there is a question. Devices may drop extension headers or transit networks. So this is one of the things we're looking at. So the extension headers themselves may be too big for the ASIC. I believe ASIC size, in the core of the internet, I believe that's 256 bytes. You can create extension headers that are quite a bit larger. And so then the question really becomes is it going to overflow the ASIC size? And there's a subsidiary question, which is this parsed at the hardware layer or software? If it's parsed in software, that may make it may increase latency, increase response time for the packet. This is a valid concern. Again, as I say, the idea of the packet is to perform a function on behalf of the application for the user, and not just to send metadata so we can manage the network. There are some potential privacy violations with extension headers. And in fact, we ourselves are working on encrypting the extension, our PDM destination option extension header to overcome some of these valid objections about a potential privacy related issue. So there's another issue, which is, again, an ongoing controversy, is whether you can change. Some people even talk about inspecting the extension header not at the source. That is, adding to an extension header in the middle of the path by some routers, say. And there are some, of course, potential issues with that. I mean, you may, in some ways, I feel like that way madness lies, right? Because there goes your checksum. The checksum is calculated over the extension headers too. I believe those are in there. So I don't quite know how you would do that. there are some valid reasons why one might. I can think of some very interesting things one might be able to do where the routers put in how much time they spent into the extension header. But again, it's easier said than done to do something like that. To me, one of the most valid issues is how extension headers are defined to start with. Extension headers use a type length value type of structure. That means you say what type of extension header it is, what's the length, and then what is the payload. And the reason is extension headers can vary in size. Having said that, the problem with this is TLV parsing is somewhat expensive to do, and especially if you want to go at line rate, and if you want to scale it. I think it was originally poor design to start with, and down the road, if I have energy, then I can, and once we can prove that extension headers can work or how they can work across the internet, this is something we may move on to, which is to have some kind of indexing or improvement of the TLV structure. That is probably quite necessary. So now to the pros. As I say, this is the side I come down on. So with any protocol or whatever anyone invents, we are human. We cannot foresee far into the future. In fact, I like a quote by T.S. Eliot, one of my favorite poets. He said, "If you can see the next step, you are doing very well." and I try to do that. I say, well, if I can at least see the next step on this path, well, that's good. And then others will arise, because you really don't know, where things will take you. There's just far too many variables. If one could predict the future, I would not be doing webinars. No, I'm teasing. I actually love doing this. I may do this anyway, even if I could predict the future, which I cannot, but no one can. And that's the thing, is no one can predict the future. You don't know what functions may need to be, what new things may need to be developed. And so if we can have an extensible protocol which can integrate this, that will elongate the life of the protocol, make it robust rather than fragile. And then, of course, our own effort, which is embedding performance and diagnostics right in the packet. This is what we'll spend a good deal of time about. I think one of the flaws in the basic architecture, well, there's two basic flaws. Well, among many, there are two major flaws, I will say, in the entire IP architecture. And one of them was not embedding security in the packet. But of course, who knew? Back in the day, we were so much more innocent. But the other problem was not embedding performance and diagnostics right into the header, which we have now done with our extension header. Yes. And there are quite a few new functions coming out for source routing and so on, which can be quite useful. But let's keep going. So there has been quite a bit of controversy whether IPv6 extension headers can really be used on the internet. And there were a number of studies which were taken to be a statement of fact, I will say, that extension headers don't work on the internet. But our experience was quite different, that when we were testing extension headers, why they did indeed work. And so then we set about to dig into Why is it that they were right, and why is it that we were also right? It has to do with the methodology they used. And so what they did, by and large, there were some variations. By and large, they sent made up extension headers to the Alexa and top 1 million, 1,000, whatever. It really doesn't matter. If you send fake extension headers to these sites, or for that matter, real extension headers to many of these sites, indeed, it does not work. Actually, this had in some ways to do with the bugs that we found, and so now quite a bit of those, if they retested, quite a bit of those would work. But that's a different thing. We'll talk about that when we talk about CDNs. But what we were thinking is, we're trying to embed performance in diagnostics. We've spent a lot of work doing this, and now we're encrypting it. But if extension headers don't work, then everything we're doing is really worthless. So what is PDM? You can go up and look at RFC 8250. As I say, essentially it embeds performance and diagnostic data. The idea is that we can see the sequence numbers that IP is using. It works across all the lower level protocols, or higher level, I should say. It's no matter if you have TCP, UDP, QUIC, whatever, ICMP, multicast, unicast, anycast, you will have exactly the same format of extension of sequence numbers and response time. The idea is you can separate server time from network time and get end-to-end response time. That's the idea. It's of course far more complex than that about how exactly you do that. But so I would suggest you just take a brief look at it. It's not terrible to read. So what we did is we set up a testing component. We have a test server enabled to send extension headers with every packet. Of course, you might be wondering how we do that, and the students will talk about that in a moment. We've got an IPv6 enabled web server, and we did that with Apache and a packet capture. So what we did is this is critical. We used a small hosting service, not one of the big ones, and we had locations throughout the world. So Warsaw, Toronto. The reason we wanted to do that is we wanted to show that things could travel across the core of the internet. And so even though there's not that many sites, but it is going across multiple transit networks, multiple ISPs, multiple exchange points, so forth. And in this case, we used FreeBSD with a modification to the kernel. We've now changed to use eBPF, and the students will talk about that. We did some real, we used a real application. We did an FTP. You can see here, file successfully transferred, and here's a trace, and this trace is showing you we're getting this PSN, this packet, PSN last received. That is from our PDM extension header. So you can see PDM extension header is there. We were also getting fragmentation. So both of these extension headers were being passed through the internet successfully. Here they are. You can see the layout. Here's destination options. And the next thing it says is chaining to the fragment header. Here comes the fragment header. So everything worked perfectly. And so this brings us up to about a year and a half ago. And so there were questions. Are these people, is your service, your hosting service, using an overlay network? So that, it's their own network throughout this. Okay, so keep in mind, this is a small, no name, if you will, hosting service. This is not Google or something. But I sent them the question, and they're like, no, we don't. We travel across the public internet using multiple transit providers. So why are our results so different? So one, I believe because we're using real data and a real application, and we're not going to the Alexa top 100 or 1,000. Indeed, if you do, there are issues. But why do we have issues? So I'll show you the topology that works, and it has a good deal to do with this. This is the 1980s or 1990s topology. This is how people think the internet works. Of course, it does not. So people think you have the client, you have the server, it's connecting directly to the internet. Well, that is not what happens. That scenario, if you do that, by and large, things work. What happens is many high usage websites use CDNs. They're also on the cloud, and that's a different story. Let's just talk about CDNs for a while, because we spent a good deal of time testing CDNs and understanding how they work and where the problem might be. So what we did is we have this web server that is sending extension header. So it's got some kind of domain name, and this one happened to have a V6 and V4 is dual stacked, so it had two different addresses. And so what you have to do, basically, to move behind the CDN, you have to give the CDN the authority to resolve your domain name. So now, instead of your domain name resolving to the address that you have, it'll resolve to the CDN, and the CDN will put it, will handle all of that. And so we'll talk a bit about CDN topology in a minute. But so after the CDN will resolve to some kind of CDN cache server, depending, of course, on where you access it from. It'll go to the cache server that's geographically closest to you. And your own server now will be called the origin server. So this is basically what we have. You have the client, you have the internet, then you have some caching server located closest to you. Probably where I am, it'll probably be the San Jose server, something like that. And then there is another. Some CDNs have their own network, but by and large, it'll again go through the public internet to get to your origin server. So this is actually from the CDN definition itself. And the way a lot of them work is that you can either serve as DNS only, or you can proxy it. And of course, and you can see the various extension headers, the various domain names we have. There was a great deal of fun was had in playing around with this and various addresses. So to summarize some of these results, if we're going to a dual stacked web server, V4 and V6, so we've got V6 from the client going across the internet, we go V6 to the CDN edge or cache server, and quite a few of the CDNs prefer V4 going the other way. In fact, you quite often have to sometimes pay more, or even it's not even possible sometimes to go V6 over to the origin. You can see here they're doing a layer 7 proxy, which many people, anyways, that's a whole different question, exactly how they're doing the forwarding. But they're sticking the forwarding, the HTTP forward header. And you can see here, this is our domain name. And this is the connecting IP, which is IPv6, and you can see here that the other side is IPv4. Some CDNs, in fact, don't even support V6 on the other side. And so we talked to one of the CDN vendors, and they say, well, force it. Just take out the V4 DNS record. And if you do that, then okay, so if you do that, what happens is that it's passed, the extension header is passed to the CDN edge, and the packet does go through, but the extension header is not sent all the way to the origin server. This is quite an interesting thing. What you have to do in order to force this is you have to force it to be an IPv6 only web server and have only a quad A record. If you do anything other than that, it'll use IPv4. It wants to use IPv4. The one thing that does work when you want to get EH to the origin server is if you let the CDN do only DNS. But then we're back to our standalone server methodology, which is that CDN is only resolving DNS, but it's essentially resolving it to our origin server. And why anyone would pay for a CDN to do this when the Google DNS will do this for free is beyond me. So anyway, so that's the story on CDN. So where we are is with 90% probability, we can say that standalone servers will work. And by and large, extension headers are not going to be sent to the origin server in CDN mediated sites, unless you do DNS only. For at least 2 of the CDNs that we've tested, packets will not be dropped. And this is a major improvement because before we started working, quite a few packets were being dropped if they even had an EH in there at all. And so what we're working with now is we're having a conversation with one CDN about possibly co-locating with them. And so then we can put up our own proxy to return the EH. That you know, as I say, that will take us a while to figure out. There are some questions though about prioritizing V6 over V4. Should they do that? We believe yeah. The other one is definitely, and they don't even fight about this. The CDNs fight about the prioritizing, but they do. CDNs, even the CDNs who don't do it, say we should be doing it. They should be doing V6 to the origin server. In fact, it was quite interesting. Such CDNs are sitting, or CDN providers are talking quite loudly at V6 up, and they're not doing it themselves. Interesting. And yet they blame enterprises for not doing IPv6. Anyway, eat your own dog food. So how can EH be sent to the origin server? That is a different question, which we'll talk about. So now let me have the students from NITK, Chinmaya, Amogh, and Balaji are from NITK. They are undergraduates, and they have been working with us. So Chinmaya, I've unmuted you. I think you need to unmute yourself, and then you can present. Okay. Yes.
Yeah, thanks, Eleni. Yeah. Hello, everyone. I'm Chinmay. I'm third year bachelor student from NITK. Yeah, so I'll be going over the implementation of PDM v2 in eBPF. So I am part of a 3-member team consisting of Balaji, Amogh, and myself. So we have been working on the implementation of PDM v2 in eBPF for the past couple of months. Yeah, so in eBPF, we use something called TCBPF, which is a subset of eBPF programs. that are attached at the QDisk level. So the advantage of using TCBPF or something like XDP is that we have both ingress and egress capabilities as compared to only ingress in XDP. And also it is attached at a point where the escape buff has already been created. So we can use this for better packet mangling capability. Also, it doesn't require hardware changes as in the case of XDP. Yeah, so coming to implementation of PDM using eBPF, the reasons that the many advantages of using eBPF for PDM is that it's easy. It's easy development and testing as compared to like kernel implementation of PDM. Also, using TCBPF, we can attach to both ingress and egress of an interface, as we have to write programs for both in the construction of the PDM header. And uh, obviously, we can modify the packet after escape buff is constructed, so that's another advantage. Also, there is an additional feature called eBPF maps, which can be used to store the 5-tuple state, which can be used to store some data that is used to calculate some of the fields in the PDM header. So what we've accomplished till now is we've explored using eBPF to add extension headers to packets. We have implemented PDM using PDM V1 using TCBPF, and we have used BPF maps to store information specific to a flow, and we are currently in the process of implementing PDM V2 in eBPF. So some of the challenges that we have faced in the implementation of PDM v2 is challenges related to encryption. So there is a lack of library support for encryption in eBPF. There's also a limit on the number of instructions, as eBPF allows for only 4 million instructions. And since encryption algorithms can be pretty complicated, it might require more than the limit that is set by eBPF. Also, there is a lack of resources of other implementations. And the eBPF verifier, it causes some errors in loading in various situations. So we have to be careful in how we code. Also, it may not be efficient due to eBPF and encryption being CPU intensive. So we have tested with XOR encryption to check if it could be done without any problems. So first, what we faced was an error of too many processing instructions from the verifier, and the error was due to setting the loop iterative variable as 64 bits unsigned integer instead of 32 bits. So the verifier would have to check for more states for a larger variable. This led to too many processing instructions. But once we fixed this, we were able to successfully encrypt PDM in eBPF using XOR encryption. So yeah, coming to challenges with the verifier checks are extremely stringent. What it does is it checks for all possible outputs of a function to verify its termination. So since the code that has to be executed in the kernel, the verifier makes sure that the function terminates by checking for all possible outputs of a function. So this may get out of hand while manipulating large data, and it might be difficult for encryption. Yeah, so these are some of the links that we refer to while implementing this.
Thank you so much, Chinmay. I'm going to keep you unmuted so that if people have questions for you, then you can answer too.
Yeah, thanks a lot. Yeah.
Sure. Thank you so much. And I see Amogh is on too. I'll go ahead and unmute Amogh also. So if he wants to talk as well, that'll be great. Thank you so much. I think without the work from these students, things would be very, very much harder for us, because they actually, it's not doing modifications. Our first implementation was doing a patch to the FreeBSD kernel, and patching the kernel, it has quite a few problems. In the end, we will probably ask, once we have PDM v2 and encryption working correctly, then we will probably ask the Linux community to adopt adopt our implementation in the kernel. But until such point, we're using eBPF. And actually, Microsoft is supporting eBPF also. So down the road, we'd like to see this on Windows. There's some actual work that needs to be done. And one of the fun things we did at the IETF, last IETF, was that we were able to sit down with actually the inventor of eBPF and Microsoft with some of the students. And that was a great deal of fun. And, we can, they were quite impressed with the work that the students were doing. And we can certainly send them some additional functionality requests if we want. That's one of the great things about going to the IETF is the connections that you make. So one of the things that we're working on now is we're starting to test cloud providers. And so far, as I said, a brief spoiler alert, we have one cloud provider where EHs appear to work to the origin, and one where they do not. And in the one cloud provider where things do not, we again suspect a load balancer that is in the middle. And we will start a conversation with them. Because as I say, one of the things we found is that the CDN provider, one of the CDN providers where things were not working, they had an actual bug, which they fixed. And I'm hoping that it is a bug with one of the cloud vendors as well. But it has been very, very interesting, and quite a few people at the CDNs and cloud vendors are being very, very helpful. So we need to test all the other extension headers. We're also we have a free router implementation where we can also add routers to this mix, and then maybe start testing the hop by hop header, which has to be, of course, done at the routers as well as the host. So, yeah, so there we are. It's been a lot of fun and great working with the students and other people. And so now I see Michael is on. And so, Mike, if you have any comments, Michael from Blue Cross of Michigan has been my partner in crime throughout all this. And so let's see if he has any comments on all of this.
Just to say that, well, first off, can everybody hear me?
Yes, we hear you fine, Mike.
How unfortunate for everybody. But I just wanted to say thank you so much for doing this, Nalini, and the rest of you. But this is extremely valuable. A lot of good work has gone into this, and we certainly appreciate you giving all this information to us enterprises who are kind of out in the dark on a lot of this right now. And to say that, as we learn more about this, I think we're going to find a lot of ways that extension headers and PDM and things in that space are going to be very valuable to enterprise operations in the future. And I think will be motivating factors for us to move to IPv6 sooner rather than later, which it might be too late to even think about saying sooner. But so I just want to say thank you. Extremely well done, and thank you for this great information.
Oh, thanks so much, Mike. It's been always great working with you on this. Well, one interesting project that we have that we've started is we are starting to work with one of the people in India who are they're putting up a test network to test DNS resiliency within India to going to the root zone servers and in disaster mode and in standard mode. And they want to integrate PDM into their testing. And so that is, that's great. That will tell you some of the results of those as well. And actually, I see one of the other co-authors of the original RFC 8250, who is Rob Hamilton, from Chemical Abstract Service. And so I see Rob is on. So Rob, I don't know if you want to say a few words. Yeah.
Oh, just a few words. This is really a good job, folks. I'm glad to see that this is progressing as well as it is. I do know that I'd like to see this, of course, implemented in some fashion on mainframe platforms. I do know that the policy agent out there does know or recognize the PDM extension header. So it's good to see that other folks are adopting or at least picking up on the PDM extension header as well. So anyway, good job, guys.
No, thanks, Rob. That is super interesting, Rob. So guys, we can let's see. That's because we're thinking one of the things we're thinking about is it's easy. It'll be easy enough to port PDM to Android. I know the students have ported to Raspberry Pi already. So we have PDM running on Raspberry Pi. So guys, let's talk offline. And Rob, maybe we can test with you, because the problem, of course, is Unix system services on the mainframe. It sometimes is not, it's not actually Linux, if you know what I mean. And so
Absolutely.
yeah, so porting it. But Rob, you run Linux under Z?
I've got one instance of Linux running under CVM. So yeah.
Yeah, let's talk offline because that I think we could relatively easily port. We'd have to recompile eBPF, but now that we know the inventor, we can talk to him, because of course the problem with mainframe, I mean, not a problem, and I don't know if Linux. We can talk offline, because I don't know if stuff that's compiled in an ASCII platform will run under Linux under Z, which is Epsidic. I've had problems with that. Do you know that, Rob?
Some of the things, some of the ASCII stuff does run. We just have to recompile it and install it into the kernel, I'm sure.
Yeah. Okay. So as I said, that's very interesting. Let's talk offline. That's a great conversation.
Absolutely.
Thank you. Any other thoughts or questions from anybody? Yeah. Students, do you have any final words? Thank you all so much for all your help.
Hey, Nalini, if no one else has any other questions, I'm just going to ask one that maybe is more along the lines of a future potential topic, or maybe one you can elaborate on just for a second or two today to see if it is. One of your packet traces, which again, by the way, I think a lot of us love that you go to the detail of having packet traces as part of your presentations, and really lends a whole new level of meaning to a lot of people. But one of them, you had a packet that was an extension header with IPv6 mobile in it. And a lot of us at enterprises are becoming more and more dependent on mobile and using it more and more. And I understand, and I say I understand because I have not tested this, but I haven't been able to, but I understand, at least theoretically, that mobile works a lot better in IPv6. And I guess my question is that true? And is it something that's worth a future topic?
Yeah, that's a very good question. And it's something, it's a bit of a morass that I haven't wanted to go into. The reason is that, the mobile IPv6 packet that I showed, it was in a test environment, and what I believe to be true, and I need to double check what the state is lately, because as of a little bit, 2 or 3 years ago, actually, it's been a while since I've looked at this. Last I looked, mobile IPv6 was not in the, it was not supported by the major vendors. So that's a problem. Where that stands today is a really good question. And if I have some bandwidth, then I'll look at that. You're right. It's very, very interesting. But if there's not support by, the major vendors, it becomes then it's a little, that's the first thing to check, right? And we can certainly write to them and say what they're doing. Am I making sense to you, Mike?
Yeah, absolutely. And that was actually one of the concerns that I had, is how widely is it deployed and by which vendors are supporting it. And, and then of course, later on in my litany of questions would be, how does it really work better than mobile in the IPv4 environment? And theoretically, it sure seems like it should, and would give us some better management and more capabilities and maybe even better performance. So I'm excited about the potential, but I just don't know enough about it.
No, that's kind of where I am too. As I say, last I looked, there was not support by the major vendors, but we can certainly go offline and take a look, because one of the things we are doing, which again, if anybody would like to help us test, that would be great, is one of the problems with neighbor discovery, and in particular on wireless networks, is neighbor discovery in IPv6, which is used every time a node connects to the network, it's excessively chatty, especially if you have a large network. If a device power comes back in, then messages are sent potentially to everybody in the network because of that. And so that makes it excessively chatty. There's other protocols. As I say, do not get me started on some of that. There's some excessively chatty protocols. SSDP and LLMNR come to mind. Multicast DNS. Both of those are using multicast. So there's some things that need to be worked on. We ourselves are working on improvements to neighbor discovery. That's the folks who are working on the free router project. More wonderful NITK students are working on that, and so ideally we can use some registration at the registration extension program, so that you're sending things unicast rather than multicast across the network. I expect probably in 6 months or so we may be able to show some of that work. But that, I think, will be very, very helpful in reducing the chattiness for wireless.
Okay, thank you. Good answer, and that makes a lot of sense. And we'll see if anybody else has interest, and maybe it is a future topic.
Yeah. I mean, as I say, it's like one of the we're working on now. As I say, I have so many things other than extension headers. What we're starting to look at is power consumption on some of these things. And of course, if it's something relatively chatty, there's likely to be a power requirement for that as well. And so, a lot of this kind of ties together. It's but as a website, I get free time, and mobile IPv6 is something to look at. Any other questions or thoughts from anybody? Otherwise, thank you so much. And thanks again to the students for all your help for presenting. And we will hopefully see you next. The next webinar will continue our security, which is more security functionality, HPKE, and continuing some of the discussion. So thanks again, and